In Krista King's video on the center of mass, you were given this problem where you asked to find the mass and center of mass where rho, the density, was equal to x plus y, and the shape was defined by the y-axis and these two lines that were given here. And she had calculated the integrals to find the mass, and she had gotten that the mass was equal to 6, and x bar had come out equal to 3/4, and y bar had come out equal to 3/2. When we look at the coordinates on the graph, x is equal to 3/4 is a little less than 1, and you can see that if the center had been at 1, that the weight should be equal, but it's obviously more heavily weighted lower than 1 than higher than 1. So at 3/4, that would put us somewhere here. And then at y at 3/2, that's 1.5, and that puts us about here. And again, from the top to the bottom, we can see that the weighting does appear to be approximately equal above and below. So what I wanted to do was a little bit of interpretation of what this center of mass is in relation to the moment. And one thing about the textbook, Stewart's Calculus 8th edition, is that the terminology that he uses is not very standard either in the physics world or in the engineering world, and so I wanted to define some of these terms. The equations are proper, but the words that he uses, for example, he says moment of inertia is equal to the second moment, and that is not true, again, if you have an engineering or a physics interpretation, because we talk about first moment and second moment. So let's first of all start off with the idea of first moment. So here are the equations for the first moment of inertia, and I'd like to take a second just to interpret this. When we look at the equations for moment of inertia, we have this product, x bar times m, and this is actually somewhat similar to torque. If you think about torque as being r cross f, the r being the length of the torque arm, and the F being the force, which is analogous to mass, we can see that we get a product like this. And m sub y means rotation about the y-axis, and so if you can imagine rotating about that axis. We can also imagine the entire mass of this plate as being consolidated as a mass of infinitely small size, but still constant mass, located at that position. And again, if we rotate it about the y-axis, we're going to imagine that x bar being the distance or the length of, in this case, not the torque arm, but the length of the inertial distance. And so you have something similar for y bar, and this equation is very, very closely related to what we have up here. But one thing to observe is that when we multiply by the opposite coordinate, what we are seeing then is that the moment of inertia about the y-axis is this integral here, but it contains that x multiplied by the density function and then dA, and I guess we should put dA also in these equations up here. Similarly, when we want to rotate about the x-axis, we are going to see then that this mass would come forward and again rotate in that direction, and the distance from the x-axis to that mass is going to be seen here. And that distance is y bar, which we see over here, and again it is incorporated as part of the motion, moment of inertia about the x-axis. So when we calculate these moments, notice that the integral contains a product of the opposite coordinate. Now, when we move on to the second moment of inertia, what we're going to do is we are going to change the exponents here. And the exponent for the second moment of inertia is going to be the second power. So the formulas are almost identical to what you originally see, except that they are going to have squares. So here are the formulas for the second moment of inertia, and I will use the notation that Stewart's book uses. one thing I should say is the Stewart book does not even acknowledge that the first moment of inertia exists, but this is the formula. Again, it's almost identical to what you see above, except it's got an x squared and a y squared instead of the first power terms. And as moment of inertia is the resistance to spinning about an axis, the moment of inertia, second moment of inertia, which we calculate again with the square, which indicates that there's some area going on. So when you actually apply some force, or in this case perhaps a mass, in a certain direction on an area, it has a tendency to distort this area and make it look like a parallelogram. And that distortion is measurable, and the greater the distortion, the greater the moment of inertia, actually the more undesirable it is for practical purposes. So for example, like when you're talking about floor joists, you don't want them to be shearing in that direction. If you want to know more about the physical properties, this guy's got a pretty good lecture online, and you can check it out. If you Google what is the second moment of area, you will find this diagram as well as the link to the lecture. But one thing that I do want to indicate is we see here are formulas for second moment of inertia. Again, I sub x has got a y squared in it, I sub y has got an x squared in it. The other thing that I wanted to point out is that here we have another formula, which is sometimes written as I0, the second moment of inertia about the origin. And you notice that there's an r squared in here, indicating that it's very likely that there's some polar stuff going on. And actually, the rotational inertia is far more commonly calculated than the x or the y second moment of inertia. The other reason why I'm not very enthusiastic about the x and y second moments of inertia is that even for very, very simple functions, they can sometimes be really messy to calculate, which I will show you an example of. So if we're asked to find m sub x and m sub y for the region that we've been working with, and the density function x plus y that we've also been working with, to just plug in the formula, we get, let's start off with m sub y. And that's equal to, it will use the same limits on the integral, but this time the function that we're working with is x squared times our rho, which is x plus y dy dx. And we get from a half x, so that's the lower line, up to the upper line of 3 minus x, and the limits on x going from 0 to 2. So this is, you know, a not too bad looking integral at first. When we integrate with respect to y, we're going to end up with x cubed y, and then plus the second term will be x squared, but then y squared over 2. And then the kicker, though, is that we have to evaluate between these really ugly looking limits between a half x and 3 minus x. And then we still have dx. And I will tell you that we don't really want to waste our time doing a whole bunch of algebra, but when you have done about probably 6 or 7 lines worth of just dealing with polynomials and polynomial integrations, you're going to end up with something like 24/5. And I can tell you that finding m of x is even worse, because when we put the y squared inside here, and then x plus y dy dx, so same function, same limits, except we have y squared multiplying. This also comes out to be really, really messy. And again, I will spare you the algebra of it, but when you end up with all of this, you end up with something that looks like 15 3/5. So the polar or rotational moment of inertia, which we have sometimes designated I0, or that sometimes it's also designated I, but we're going to make an analogous comparison between linear and rotational energy. perhaps it makes more conceptual sense to say that energy is proportional to the mass, and similarly that the energy required to rotate is proportional to the inertia. But in any case, we have these formulas. Kinetic energy is equal to mv squared, where v is the velocity, and it's calculated as ds dt. And analogously, we can say that kinetic energy to rotate something is 1/2 I omega squared, where omega is equal to d theta dt, and that gives us the angular velocity. Now, one thing to note is that when we convert between linear and rotational, that just as s is equal to r theta, we can also say that v is equal to r omega. And what that means is that if we wanted to calculate 1/2 mv squared, the kinetic energy in the linear direction, that if we did a substitution here, and we have then that v is equal to r omega, we're actually going to end up getting r squared omega squared. And so there is a proportionality here, but you can see we have this factor of r squared that's inserted. And so what we find then is that if we want to find the rotational inertia, it is going to be the sum of all the masses. And so if we have, again, some masses that are distributed and not just in some ideal unified blob at a certain distance, that this is actually going to be the sum of those masses, but multiplied by r squared. And the implication for that is that when we calculate the integral for the moment of inertia about the origin, that our integral is going to be the double integral, but it's going to have a factor of r squared in it. And that r squared we can indicate as x squared plus y squared, but and then times our rho of xy dA. But this additional factor, it's not just x squared, it's not just y squared, but it is that factor of r squared is inserted here. And we didn't really explicitly talk about last time, why did we put this x squared in there when we were calculating the the second moment of inertia? And it again had to do with the area, but we can see when we're doing the rotational inertia, it's much clearer as to why this factor of r squared appears. Let's finally look at a problem that might look something like the type that you would see in the homework. And so this is actually a row here. So it asks to find the moment of inertia of a lamina covering the unit circle where rho, our density, is equal to 1 minus x squared minus y squared. So we are going to perform the double integral and say that this is equal to, and again our rho is 1 minus x squared minus y squared. And we are going to put in that r squared factor, which would be x squared plus y squared, and then our dA, which is in terms of x and y, we would write it as dy dx, or the reverse. However, we really don't want to keep this in Cartesian form. We would like to convert it to polar. So let's do that. When we have the double integral, our x squared plus y squared, so this is in parentheses, but that's going to look like r squared, and then our rho is going to look like 1 minus r squared, and remember that dA is going to come out as r dr d theta. Next, we want to figure out what the limits on r and the limits on theta should be. And because it's a unit circle, we can see that the radius is 1, but we want to cover it over the entire area of the circle, including the interior, which means that our r is going to go between 0 and 1. But our theta will go all the way around the circle from theta is equal to 0 all the way until theta is equal to 2 pi. So now we just need to simplify our expression, and as we put the various terms together, so I have an r squared times a 1 times an r, so that's going to give me r cubed, and then minus, we have r squared, and r, that's going to give me r to the 5th. And again, integrating, so we have dr d theta, and we go from r from 0 to 1, and theta 0 to 2 pi. So simplifying this, we end up with r to the 4th over 4 minus r to the 6th over 6, evaluating between 0 and 1. Still integrating 0 to 2 pi on the d theta, and letting r equal 1, we get a 4th minus a 6th, and then we subtract off 0. So 1/4, let's do it on the side, minus 1/6, LCD of 12, so we get 3 up here and 2, and so that's going to give us 1/12. And that's all that we end up with inside. There's nothing that's a function of theta, so we get just integral of 1/12 d theta, 1/12 d theta, and that's just going to give us 1/12 theta, and we will evaluate that between 0 and 2 pi. So we're going to end up with 2 pi minus 0 over 12, which is equal to pi over 6.